Okay, this is problem 11-4. So in 11-4, there's a wire with a current I over here, and there's a rectangle that has all these dimensions A, B, C, all that good stuff, and that's considered up. So part A is asking what direction is the magnetic field inside of this loop due to this current from the wire. So using your right hand rule, the current is traveling to the left and your fingers curl around. So the magnetic field is the fingers curling around. So the magnetic field would be coming, yeah, the magnetic field would be coming out of the page over here because it's going like this and into the page over here. So over here it's out of the page, so that's the answer. Out of the page. B. So this is actually kind of complicated. In terms of those, A, B, C, alpha, beta, and fundamental constants, we have to determine an expression for the magnetic flux through the loop as a function of time t. So we're going to use this equation. It's on your equation sheet. B equals mu naught I over 2 pi r. So if we plug in the I that they give us right here, we have B equals mu naught alpha times 1 minus beta t over 2 pi r. So that's our equation for B. So then switching gears kind of, we have another equation where flux, magnetic flux, equals the integral of B dot dA. So in this problem, the dA also equals C dr because the area just equals the length times the width. And the only thing, it's the C is constant because this is never going to change. But for the magnetic field changes based on how far away you are from this current. So the dr would be like this, dr. So that's the same thing, it's just length times width is area, so dA equals C dr. So again, we have flux equals, oh, it would also be from A to B because that's just how big the rectangle is. That's where we're taking the integral. So it would be, so the integral from A to B of, using the B that we solved for up there, mu naught alpha over 2 pi r. Then if we make it like this, 1 minus bt over here, it just, I don't know, it makes it easier for me to see. And then C dr. So if you take the integral of this, everything in this is constant besides the r right there. So you have mu naught a over 2 pi 1 minus beta t, and then the integral of a 1 over r is an ln of r, and that's evaluated from a to b, like that. A to b. Oh, and there's a C there, thank you. Sorry, the C just goes dA is C dr. So the C goes from here to here, sorry. So dA equals C dr, then everything is constant including the C, which moves down there. So r is the only thing that's changing, ln of absolute value r, integral a to b. So then you evaluate the definite integral, so you have all that all over again. You get ln of b over a. It's ln of b minus ln of a, and that simply goes to ln of b over a. And that is your answer for the magnetic flux, and that's part 1 of B. So part 2 is asking us the magnitude of the induced EMF in the loop. So we have the equation EMF equals the negative change flux over change of time. So we solved for the flux up here, so E, shoot. No, don't die on me, pencil. E equals negative mu naught alpha C, oh my god, over 2 pi, then there's ln of b over a. Oh my god, this is insane. Ah! Ln of b over a, and then the only thing that you're taking, it's the d dt, right? So d dt, the only thing that has time in it is 1 minus beta t. So then after taking, that's all the same still, so The flux is that, the derivative of the flux is that, that's the change in flux, which we solved for up there. Then the change in time, it's over the change in time. The ddt, the derivative of this, of t, is just a negative b. So it's all this minus b, or beta, sorry, then ln of b over a. And that EMF equals negative mu naught alpha c beta over 2 pi ln of b over a. For part C, could I borrow a pencil?
Yeah. What did you do with that pencil?
No, that's okay. Okay, writing switch. Part C, it gives you part 1, you have a rectangle. It says beta t is less than 1, and it's asking you for the induced currents in the loop for each of the following cases. So for I, bt, this is basically the time constant. So I is always getting smaller throughout the entire problem because t is always getting greater. So because I is getting smaller, the induced current is this way because of Lenz's law. It has to counteract the change of flux by making it go like this. So your induced current will look, yeah, it'll look like that. The induced current goes around like this. And then it's the same thing for part 2, where bt is greater than 1. The I is still getting smaller just because time is passing. The I is always getting smaller, so the induced current is still this way, going around clockwise. So then it's asking what's the direction for D. It's asking what is the direction of the net force, if any, on the loop due to the induced current at I. So that can be attained. You can figure this out using the right-hand rule. So over here, the induced current is going this way. So if you go like this and like that, you know the magnetic field is going into the page. So you go like that. And then that's the current, that's the field, and the force is down. And that's the answer. Down. And that's problem 11.4.